Okay, so can everybody hear me? I think I'm hearing my own echo.
Yes, we can hear you.
Okay, so I hope most folks here on the Zoom link have access to Blackboard. So what I'm going to do for the first few minutes is just walk through the logistics of the course, and then we'll actually get started. Okay, and at any time, if you have questions, you can certainly ask me using your microphone. You can keep the mic off throughout the course, so throughout the lecture session. When you have a question, you can unmute yourself. There is no requirement to also turn on your camera, but you're highly encouraged to turn it on, especially when you're speaking, so that everybody else knows who it is, and including me, who it is, and understand the question. Okay. And also during the session, feel free to turn on. You can turn it off. You can. It's your choice. Okay. So I hope everybody can see my this browser page where I'm showing you the GitHub link. So how did I get here? It's basically, sorry, let me go to the course. Okay, so what happened? Okay, so this is how it should look like, hopefully for all of you. There are basically 5 key links. Let me walk over them. First one is the syllabus page, which is just a simple page, which links to the syllabus, which is this link. And so we're going to discuss that in a second. The second link is a Zoom link. I hope all of you can see the meeting invites. They're recurring invites every Monday, except for next Monday, which is a holiday. And you can just use that to come back to this, or you can just save the link. It's the same link every week. Okay, the third one is announcements. It's basically just a archive for announcements if they're sent from the TA or myself. You'll get the email. You'll get the email to your inbox, as well as the announcement will be archived here in case you wanna have a ready access to the email. Okay, or the announcement. The fourth link is uploads. And I'm going to walk over all of them, the details and so on, but uploads is basically, as the name suggests, it's just uploads for assignments and other things that are there for this course. Okay, and we'll discuss that in a second. And the last one is a discussion board. It's just a board, it's a feature in Blackboard. Haven't really used it much myself in my previous courses, but if folks in this course are interested in using this discussion board, then we can use it. Okay. And if you have questions, I have the chat window in front of me. You can always use the chat or unmute yourself and talk to me. Okay. So what I'm going to do is next actually go over the content of this course and what are different moving parts here. So this is IDS 575. So in case you're in the wrong course, this is a good time to check. I'll actually go over a few of these in the lecture slides that I've shared, but let me come to that in a second. So what is the overview? I'm going to give a very brief overview, a teaser, because I'm going to talk about, again, a little bit of logistics in the slides. So if, as the short introductory paragraph says here, it's basically a course which tries to complement, 572. And 572, you might have seen a lot of applications and a lot of techniques of various types of data mining as well as machine learning techniques. So this course covers the foundational, I guess, jargon and terminology and the way of thinking that you need as you interpret different models, new models or new modeling techniques come along, every year. So it gives you a nice base from which you can understand and relate it to things that you already know and so on. Okay, so it's more about the foundation of machine learning. And there are some previous versions taught by me, which are linked here, but also, of course, Professor Munte Lee has been teaching this recently. So you may have, some of your friends who have taken his course are also simultaneously taking his course. The lectures are now 3 to 5:30 p.m. They are actually on campus, but today we are online. The staff is myself, and we have a wonderful teaching assistant, Parshan. He's a PhD student in the department and has taught this course several times and is really good. And so do reach out to him if you have questions during his office hours and recitations. Okay. So my office hours are on Thursdays. Sorry for the typo here. But my office hours are on Thursdays, and office hours for the TA are, I have to update it. I think it's on Monday evenings or Tuesday evenings. So I'll just update it based on what the TA has communicated with me. So I'll update this information here. So next is a huge list that I just made here. So it's a very short, it's a very succinct list, kind of tells you what's going to happen each week. Okay, and when are assignments due and when are some other things due. Okay, so as you can see, we are here on Jan 10th. There's a bunch of lectures that are going to happen. This course is a little bit different from some previous editions by myself as well as by Professor Lee. Here, I'm going to be focusing more on assignments and projects. Okay, so you'll see that there is no time slot for a midterm exam, for example, in this list. But instead, there is actually a slot for meeting with students, okay, on projects. So we'll talk about that in a second, but this is the timeline. And if you have any questions about this timeline, you can ask me right now or on chat, okay? But I'll continue. So the materials for this course, actually most of the materials are provided, have been iterated and have been provided here, which are two free to access books. So you can just get them online from the respective authors pages or the respective book pages. But the material that we're going to cover in the class is mostly based on the slides. Okay. So I hope everybody can access the slides, and you can see all the slides are in that folder. So the slides will be maybe updated slightly as we move along in the course, and there is both the slides in the PowerPoint version as well as in the PDF version. Okay, so they are basically the same. There's going to be a growing list of additional readings, and I'm going to comment about this in a second. Actually, many of the first good chunk of links, but this is just an initial set of links useful to augment your I guess, exposure to business analytics and particular machine learning as well in this course. Okay. So in particular, let me focus on a few of the links here. So the ones I highlighted, and it's pretty bad highlighting on the browser, but the ones I highlighted are related to some prerequisites that you would like to have when you're taking this course. Okay, so you should ideally have it before. If you're weak on a couple of these things, it's a good idea to check out these links and get up to speed. Okay, it just gives you the vocabulary and the familiarity when we're going to kind of use some of these concepts. Okay, so our course is not about really becoming experts in probability or experts in linear algebra, but you want to know the basics so that you can use it in the class. Okay. So there are basically three directions. One is probability, one is linear algebra, the last one is calculus. Okay, so those are the three directions, and we'll briefly mention it again in the slides. So we'll get to the topics in a second when we get to the slides. Let me just cover the other logistics. So there is a link here. So this actually is a link only, I guess, only open to UIC students, but basically you need to form a group of 4 students to complete both the assignment and the project, and it's the same group. Okay. And so to reach out to your classmates, there's a spreadsheet. You can add your name. If you want to add your skills as well, you can just extend and add a column there. So it's just a simple spreadsheet to create, seek out other folks if that's the only channel. Otherwise, you can also seek out to other channels. And once you do that, you want to enter your final group list of names as well. Okay, so it's not just to seek out other people, but also that spreadsheet will have the team members of the group, okay, for each group. And so let's talk about assignments and projects. As I said, the course has been slightly updated, and I'm experimenting with this format where the focus is going to be on assignments and project. And the project is not going to be just a nominal project that, it's just like 10 credits or something. It's a big chunk of this course. So there are going to be 5 assignments. They're released on GitHub. I mean that there's going to be one more markdown file or whatever, like an IPython notebook that will be in this repository. Okay, so and I'm going to mention that when I release the assignments. So assignments are going to be released approximately 2 weeks before the assignment is due. So the first assignment is actually due early next month. So we do have some time to get up to speed on the prereqs. Okay, so the reason why the first assignment is a little bit a couple of weeks later is because I really want most of you to spend time on the basics, because once you have a good understanding of the basics, everything else will be like super easy. Or at least you will be familiar when we are discussing different topics. Okay, and the topics, some of them you might have already seen. We're going to talk about it in a second. But if you do the basics really well, it's going to be easy to communicate with the TA, with myself, with other folks. The nuances of these methods. So let's come back here. There is not going to be any extensions for the assignments. So there's a simple rule here. You just get 20% off on your grade. I hope it's an acceptable trade-off. So try to pace yourself beforehand. Okay, so don't keep things at the last minute. Assignments is going to be made available as soon as possible. So you will have enough time, and in fact, you will have approximately 2 weeks between assignments. And so pace yourself properly. Okay. The big second component of this course is a project. It's basically, I think most of you have, if you've done for 572, you would have an experience with working through a project in a team setting. So it's a similar setup here. The objective is to really demonstrate on any data set of your choice, and of course we're going to have check-ins so that we have feedback for you on whether the project is the right level and so on. Basically, you want to demonstrate your expertise in gathering the data, doing some exploratory data analysis of this data set, doing ideally some prediction modeling, but you can also you can define a scope to be only exploratory if you want, and communicate some key results, observations, and so on. Okay. So there is some details, some more details on the project page, which tell you how the grading rubric will be for the project. Okay, so basically there's going to be 4 components that are listed in the project page. I encourage you to look at it. Let me mention the 4 components. Basically, correctness of what you did, content, creativity, and clarity. And these few pointers here kind of elaborate on what exactly we mean by that. And so in terms of the split up, there's 5 assignments, so about 60 points. And the project is about 35 points. There's an intermediate report, I think 2 or 3 pages that submit, I think, around March. And then there's going to be a final report submission. And the last couple of lectures are reserved for you to present your project. So as I said, this course is really kind of minimizing exams and focusing more on really working through a really interesting data set of your choice and accomplishing something by the end of the course. Okay, so there's also a few minor points on course participation, which mostly are about try to attend every class, try to interact with the instructor and the TA, and also, and most importantly, actually, how well you support your group. Okay, so please don't be inactive because somebody else in your team is carrying through everything. That's not the ideal we want to achieve. So try to support your group well. Okay. So any questions about these logistics?
Hi, Professor.
Hello.
Hi, I'm Shravya. I have a question about the mode of instruction. So once you start teaching on campus, is there any option to attend online in case we're unable to come to campus? Is it synchronous?
Yes, that's a good question. So as it says here, so if a course is, if the lecture is online, it says online only. So you can see that some of the, actually some non, like for example, your presentations, it's not necessary that everybody be there in person in the classroom to listen to other students' presentations. So these are online only. Like I have plans to meet individual teams on this date, and so those again, for 15 minutes, nobody needs to come for just their slot to the campus. But most of the others are nominally on campus, but students are free to listen through online as well. So I'll have a Zoom meeting simultaneously going on. So you can come in, and these, by the way, another big point is this is going to be recorded. So if you if you have some non-course related discussion you want to have, then we can have it offline or through some other channel. But basically, this is going to be recorded and it's going to be auto-populated on your Blackboard after the meeting. Okay, so you can, if you miss a class, if you can't be, this is going to be synchronous. So if you miss a class, then certainly you can go through the recording, but try to attend definitely, ideally on campus. If that's not possible, try to be remote. If that is also not possible in some extreme cases, you can certainly listen to it afterwards. Okay. But as I said, the evaluation is mostly, so if some of you, and you can see some of the list here, and some of you may be very familiar with some of these topics, that's fine. We will, again, tease apart through each of them and understand them in a little bit more detail. But the evaluation is mostly based on how well you do in the assignments and your projects. So, and in particular projects, since it seems a little bit open-ended at this point, as the way I have at least mentioned it, really focus on that and talk to the teaching staff to get to get a good part for this component of the evaluation. Okay. Yep. So if there are no questions at this point, I'm going to switch to slides. They also walk through a little bit of the logistics, so on particular topics. So we'll maybe come back to this, I guess, again. Okay. So I'm not doing full screen. I hope you can see, I guess you can see the top nav bar as well, but I hope that's okay. Is everybody able to see the font size and this particular slide deck? It's fine, right? Okay. So if needed, I can make it full screen, but I don't think it has minimal distraction at this point. So it's okay. Okay. So I went through a little bit fast when I was talking about, hey, how is it different from, let's say, 572 or maybe some other courses that you will take or you're taking simultaneously to this. Primarily, as is mentioned in this slide, the objective is to really seal the foundational base, okay, for understanding these machine learning methods. Okay, not just the methods that we'll discuss in this class. You kind of will use the same vocabulary even when talking about something like deep learning methods or some other unrelated, some other methods that we'll not see here. Okay, so it's to establish that strong statistical machine learning foundation. And so in that sense, it's a theory class. By which theory is just, it's all relative. So theory just means that at least in the, we will not be too embedded into how a data set looks like or how we can achieve a little bit more performance while doing predictive modeling and so on. We'll be really focusing on the foundations. Okay, that's what I mean with theory. The applications, you will kind of get exposed to them through the homework, the assignments, as well as the final project. Okay, so the class it's a large class, and there's the heterogeneous levels of background experience and prerequisites that everybody has. So one, the formal prerequisite is certainly statistics for management, and or something equivalent that you might have taken. But we do have some other prerequisites, which is what I mentioned earlier. You need to know calculus, in particular multivariate calculus. It just means functions of multiple arguments or multiple inputs. You need to know what a gradient is, what a partial derivative is, or basically in general functions of two variables. Okay. First of all, you should be familiar with what is a function, and then functions of more than one variable. And so many of you already have experience in this, informally at least. Like every time you plot a graph, it's a function of let's say one variable, like time versus sales. It's a function of one variable, right? So we'll see this, but in general, having some good familiarity with calculus will help. The second one is linear algebra. So here we will use the notion of a matrix. So you want to understand what a matrix is, and what is a linear equation, or what's a linear system, what are eigenvalues and eigenvectors. And that's, I guess, a little bit more advanced topic in linear algebra, but it'll be good to know what eigenvalues are and what eigenvectors are. And matrix calculus, by which we just mean, if you transpose a matrix, if you invert a matrix, or some other properties that matrices satisfy. Okay, so for example, symmetric matrices, if you just if it's a matrix symmetric, if the matrix is equal to its transpose, right? So simple identities like that, but in general, and also the last bullet point covers matrix vector multiplication and things like that. Okay, so that's what are some three examples here. And the next topic is probability. Although we say probability theory, informally we just mean a good undergraduate level understanding of ideas in probability. We just mean, hey, what is the probability of an event? What is meant by conditional probability of an event A given event B, or a conditional probability of a random variable taking some value given another random variable. Okay. We'll also have it'll be good to know what is meant by likelihood. We'll see that when we get to some methods, like let's say Bayes or logical regression. We'll come back to this idea, but it'll be good if you have at least a sense of what is the likelihood. Okay, likelihood is just a probability or a conditional probability. Okay. Similarly, there's this notion of entropy. When we look at decision trees, we'll have this notion. We'll visit this notion, but it's good to know. And also some univariate distributions like uniform distribution, Poisson distribution, Gaussian distribution, like in 2 dimensions, like a Gaussian distribution, 2 dimension looks like a bell curve if you look from the top. So or concentric circles if you look from the top. So these are notions that will be good if you have some exposure. And for homeworks, for the assignments and the project, the language of choice is Python. So you want to have good exposure to writing non-trivial Python programs. So we mean even if you know the basic constructs like dictionaries, for loops, if-else conditions, and lists and so on, using them is good enough. So that, but to use them effectively is what we mean by non-trivial here. And ideally, if you know some basic data structures and algorithms, it's good, but it's going to be case by case basis. But the point of this last prerequisite is you need to be comfortable with Python. You can't be learning simultaneously Python in this course and doing the components of this course. Okay, ideally you want to learn Python maybe through some complementary course or from beforehand. Okay. Okay, so with that, let me just summarize. So you want to check your enrollment status, have it correct on both UIC system as well as on Blackboard. If folks don't have access to Blackboard, you should get it soon. If not, email the teaching staff, either me or Barshan. So dates have been listed in the syllabus page. So do definitely cross-check if you have some conflicts on those days and reach out to me beforehand, me or Prashant beforehand, as early as possible. Announcements will be made under, as I think I showed you earlier on Blackboard. There is an announcements tab. You will see historical announcements there. Be prepared with the background material. So actually the first two clips, first two links there, probability refresher and linear algebra refresher, are something I recorded a few years ago. So have a look at them. They're very short. So it'll give you some, I guess you'll be able to get up to speed, at least on probability and linear algebra. And try to use office hours. Okay. And I guess most importantly, try to form teams. And that's also another reason why the first assignment is a little bit, a few weeks from now, so that the first week or two, you kind of galvanize towards forming the group. Okay. And this is not a decision you should make it quickly. So try to make groups where you have similar schedules and so on, so that you're not time constrained. Okay. Okay, so with that, let me, so today is going to be mostly motivation. So the outline is first motivate what is the context in which we are learning this topic or this collection of topics. And then, an example of, teaser on what is machine learning. I think many of you have done 572, are pretty familiar on this side. And then there's some, some sampling of recent or the past decade, few things that have happened in machine learning, just to give you a sense of how it's very impactful in the commercial world, in the industry, and then what to expect in this class. Okay, and we'll try to get to lecture 1 slides today as well, which is going to cover random forest and which is going to cover k-nearest neighbors and decision trees. Okay? So as two methods for a specific type of problem. But let's start with some motivation. Since the advent of machines or computers, especially since post 2000, right? So even early 90s, there's been a lot of areas where computers have permeated, computation has permeated, be it construction to marketing to agriculture to healthcare and so on. There are many, many different areas, and all of them are getting digitized, and there's not machine learning but per se, but there's a lot of data collection, some stats, some that's always happening, reporting or forecasting or something like that, right? So here are some examples, right? So and this is just a scale, give you a sense of scale of how much data is being generated. Really, it's the era of big data in 2022, and that's because, and these numbers are actually a few years old now. It's probably like you can add a multiplier of 2 or 3 there. Like for example, this Facebook, for example, has 300 million photos per day. Okay, so that's an insane amount of photos. Similarly, YouTube has 300 hours of videos uploaded per minute. Okay, so you can get a sense of, okay, if it's 3-hour lecture, that itself is quite a bit. Now you can think of 300 hours. And then that's per minute, right? So the largest outlier platforms like these are really, getting drowned in data, and they have that engineering and resources to be able to deal with this scale of data. And there are, of course, other interesting applications like Google Home or Siri or Alexa. They also have a huge subscriber base and a huge amount of data, audio data that they work with. Similarly, if you think of other social networks, microblogging platform like Twitter, the number of tweets and the number of comments on these platforms is really large. Okay, it's not. So if you're gonna, as you'll see in our projects, we'll probably be looking at 1/10 of this data. 1/10 of this data of a single day. Okay, although these platforms have been there for years now, and you can imagine the 1000x or something like that multiplier in terms of the amount of data that they have. Here are some more examples of similar being in the online world. So Amazon, if you think of reviews or reviews, for example, on Amazon's website, or on something like Stack Exchange, the number of questions, number of comments, number of votes, it's already, all of these data points that have been measured and logged, they amount to millions, right? or and their impact on revenues of these companies. For example, for Amazon's case, is in multiples of billions. Okay. Similarly, on the video or music side, there's platforms like Netflix and Spotify with huge subscriber base. These are all outlier companies. I'm not saying that all companies have such a scale, but given that that's the that gives you a sense of like what is the level at which some corporations are working on, not just these firms in the US, but also firms in China, firms in EU, firms in India, to name a few. They all, at least the biggest firms like these have to work at the scale, right? Let me give you two examples. As I was saying earlier, data is not just related to these tech companies, but also in many other areas of life, from science to education to health to sports to manufacturing. So let me give you a manufacturing and a science example. So in manufacturing these days, or not just manufacturing, but these days many devices are actually connecting to the internet. So they are able to speak to other devices and devices elsewhere, to servers, to update themselves and so on. So there's really, and if you think of devices, each person probably has way more than 10 devices on average. I'm just, if you look at a statistic, maybe they have a lot more. So all these devices are connected with each other, exchanging information, and so on. So this is something that was not there, for example, even 10, 20 years ago. Similarly, if you think of science, previously it used to be, or before, even before, in the last century, for example, much of work was more, I would say, interpretable and simpler, in the sense that you would have formulae, equations, which govern phenomena. Like, for example, if here I'm just showing you the law of gravity, or Newton's laws. But these types of interpretable or simple equations of systems, equations of such physical systems, they are not possible anymore. And so if you actually want to really understand and track and predict physical systems, then you do need today at least computation tools. And so computers and data and processing data is kind of necessary to make advances in science. Okay. So just the second example of trying to show that we are really in the era of really large data sets. Okay. So we have large data sets, but this course is not so much about how to work with large data sets. We have a different course for that. But this course is trying to use tools that can work with these data sets, whether they be large or small. You want interesting tools that can do interesting things. And so that is what we'll be looking at. And the tool set is basically the set of machine learning tools. Okay. So let me just briefly motivate what is machine learning. And for folks who have already done 572, it's just a simple example. But let's still go through it. Okay, so this is a very textbook example. So let's say you want to take a class and you don't know how it will be graded, but you'd like to, of course, get good grades. And let's say you do know that the grades are a function of, or are evaluated based on performance in homeworks, performance in exams, performance in attendance, projects, and so on. But we don't know exactly the relationship between how well you do in these components to what grade you'll get. But what you do have is a data set. Okay? And what is the data set? The data set is basically how people did in for example, these components, and what grade did they get. Okay, so something like this. So so Alice, for example, has some value for participation, some value for homework, some value for project, some for exam, and then eventually she got a grade A. Right. So you have a table like this, and each row in this table is considered an instance. Each row is a data point, an instance, an observation. Okay. And each and these 4 features or attributes here are called attributes. So that's, I'm just introducing terminology. Okay. So these are descriptions about these characteristics, like what is the participation? It's either enthusiastic or modest or silent. Okay. And although this is a realization, this is a particular data set, you can talk about the instance space. It's also called the input space. So let's talk about the instance space, which is a set of all possible features, all possible attributes that you can have. Okay, this is all possible inputs, for example, to your machine learning model. The label space Y, again, is very similarly, is just a set of all possible outcomes, all possible classes that that can realize. And an example is a pair of instance and its label. So earlier when I said instance, I was talking about a row, but you can ignore the last column here. The last column is related to the outcome, okay, or the label. So example is a pair of instance and a label, x comma y. Okay. And so this table here at the top, we're going to use the notation capital D to represent the data set. And each row, so row number 1 will be represented using the pair x superscript 1 and y superscript 1. And so the ith row, like I said, the third row will be x superscript 3 comma y superscript 3. Okay, and those 3 are in brackets. Okay, so just to give you a feel for like the notation here, but that's I guess the description of inputs and outputs are basically attributes, instance, label, and an example, okay, and the data set. Now, what do we want to do is we want to, so what we'll do is we'll assume, okay, that there is some underlying relationship, okay, between the input, between the instance space X and the label space Y. Okay, there's some relationship, and in fact, it's a function that maps from instance space X to label space Y. Okay, and that function is the one that has created this extra column. Okay, so the red column that you saw in the previous slide, and that function is the one which did it. Okay, giving us the training data D. And what we want to do is find some function h, okay, which again goes from instance space to label space, in particular from whatever be the collection of attributes, attribute values to this value +1 or -1. So that function that either imitates f or approximates f. Okay, so that's as close to f as possible. Ideally, you want to, if f itself was, you could find it, then of course you would want to find f. But maybe f itself is not exactly, you don't know f itself, but you want to get an h which is as close to f as possible, like ideally imitates f everywhere. Okay, so just to, as I said earlier, instance space X is called the input space, and Y is called the output space. Okay. And so in a sense, machine learning is just a way to find this function, h. Okay, so either you can think of it as a black box, but we'll open this box throughout this course, but it's a, think of it as a black box for now, or an opaque box where all you're trying to do is, given this data set, find this h so that h imitates or approximates f. Okay. So that's one very popular problem in the collection of, I guess, ML problems. Okay, also called supervised learning. But that's an example of machine learning. An example of machine learning. We'll look at other examples throughout the course, and maybe later part of this course. But that's just to give you a teaser of, when we talk about machine learning, that's the terminology, for example, we use in the previous 5 minutes, right? We use some notation, x superscript I, y superscript I, a notation like this, right? So f colon x right arrow and something like y here. So there's some notation that we've used, and it's just a way to communicate what we mean. And this is where, as I said, the prereqs will help you get familiar with writing something like this. Using, for example, when you go through calculus. And so this notation is kind of useful. Okay, it gives you common language to communicate with other data scientists, business analysts, and so on. but that's not the focus though. The focus of this course is to really understand the statistical underpinnings of different methods, and we'll see what methods those are. You'll see that there's good overlap with 572 in terms of those methods, but hopefully we can offer a statistical perspective. By statistical perspective, I mean we can define random variables, we can talk about expectations, we can talk about generalization in a more formal sense, and so on. So let's now briefly again step back and talk about why should business analysts do or data scientists do this course, right? So why spend so much effort in machine learning? So why can't we just spin up a Jupyter notebook or whatever and eventually start digging into a data set and so on? Okay. And that's because there's a lot of nuances when you want to apply techniques in the real world, and there's so many applications in the real world that you can't really go through all of them. So it'll be good to extract out the most generalizable ideas and patterns and talk about them, and that's what this course is. But its impact in the real world is quite a bit, right? So, and that's what I want to briefly mention now. Over the past 10 years, few tidbits of things that have happened, right? And this is really early years of early part of last decade, when deep learning really took off with the creation of some really good object recognition model back in 2012. So here's an example where back in 2013, Google acquired a company based on company founded by some professors or from researchers at the University of Toronto, which eventually became, I guess, Google Brain. And there are very similar examples elsewhere. For example, even earlier before that, there are other activity in the commercial world that is happening. For example, there's some AI startup. This is just an example. Some AI startup got acquired by some other company here. I guess it works on natural language processing. And similarly, there was a company called Alchemy, Alchemy API or Alchemy.api, which got acquired by IBM. And this is all, about 8 years ago. And in fact, I guess 8 years ago or 9 years ago, Facebook created a new lab, okay, FAIR, I guess, FAIR. So which brought, started hiring a lot of researchers to advance methods for machine learning. And you'll see, if not in this course, some other courses like the deep learning course, Facebook has contributed a lot. Like, for example, PyTorch is a good example of a package in Python that a lot of people use to build deep learning models. So, so the creation of this type of labs and these types of acquisitions kind of show you how much machine learning models hit the ground. Okay, but before hitting the ground, you want to be solid on the foundations. Here's another example. I think some of you might have seen Professor Andrew Ying's course on Coursera on machine learning, actually. So here's excerpt from 2014 when he, I guess, joined, Baidu, which is a search engine giant, I guess, back in 2014. And of course, all tech companies kind of did very interesting things then. There were also interesting breakthroughs. So the ImageNet or the image recognition model built in 2012 really improved the status quo quite a bit. Okay, similarly, in terms of speech recognition, there was a big jump in the performance. Okay, so lower is better. So big jump in performance using deep learning models in particular around 2010, 2015. Okay, compared to the way we were doing machine learning before. Okay, so it doesn't mean that the way we were doing machine learning before is incorrect or anything. All of these are based on the same statistical ideas. Okay, so you need to have that foundation to be able to maybe further improve in the future. Okay. Here's, I mean, so these plots are just showing a particular performance. So think of the y-axis as like a error. Here it's particularly word error rate on a particular data set called switchboard data set, but for us, the details are not important at this point. And here it's just showing different types of models and what the performance is as a function of time. Okay. Okay, and there are many applications that have been possible today, thanks to machine learning, that you wouldn't think of when you just have computers. Okay, in the sense that what we couldn't think of in 2005 is possible in 2022, right? So, for example, here we can correctly label, that there's a person here, there's a dog here, there are other people here, and that was the I guess one of the famous challenges that happened is called image net large scale visual recognition challenge, which is where, as I said, in the last decade there was a huge improvement thanks to not just machine learning but in particular deep learning. And more recently, I think in 2016, there was a ML based software, AlphaGo, which was able to compete with the number one player in Go at that time, Lee Sedol, and I was able to defeat that person. Okay, and this was a significant achievement, very similar to how there was an achievement in chess and in other game domains. But this was significant in the sense that you did need those machine learning innovations to be able to design this, which could do well, right? And since then, the machine learning models have been improved upon consistently. Here's another snapshot of the same thing. So this is in particular for the game of Go. A similar model, maybe an iteration victory over another world champion, KG. And similarly, other applications, which again, as I said, were not common, about a decade ago or 2 decades ago, are common now. So you can see something like image captioning, where image is input and you can automatically create a tag or a caption for that image. Okay, and in between sits a black box. Okay, the same ML box, which can take this as an input, somehow create a bunch of attributes, and then create basically a label which looks pretty complicated, but at the end of the day, it's going to be a label, right? Similarly, we can also do more crazier situations, like given a picture and a question, that opaque box can also say can answer that question. Okay, so to answer that question, you really need to understand the image, and so and some researchers have been able to achieve that. Similarly, in this is a much more complicated setting, which is called visual dialogue, where you start with an image and then the machine tells what's going on in the image. You ask a question, and the machine kind of needs to understand, what the question is about, given the image and what it understood, to say that the umbrella is black. Okay, so it's like humans can do this, but to make computers do this without memorization, of course, this is let's say instead of this image, you give a random test image, still be able to do this, have this dialogue. Okay. Okay, so a couple of examples in the image area. So there's this interesting machine learning modeling technique. Okay, it's called a generative adversarial network. So don't worry about the words. The word generative should ring a bell to some of you. Some of you have taken 572. There's this generative models and discriminative models. So think of generative models as being able to generate, data points, basically. So here, this particular modeling technique is able to generate new data points. In this case, it's going to be it's going to be images. Okay, so it's able to generate. So the thing on the left, these red boxes. So in the red boxes, these images are real images, photographs, and the ones on the right, this 4x4 box, are generated images, which are slight variations of these original images, where like if you take the original image, I don't know, if you want to change the gender, if you want to change the age, if you want to change the skin, then it can create a new image which looks pretty realistic, but it's not really an image from a data set. Okay, so of course there could be hand-based rules which can do this, but here it is done using a machine learning model. Okay, so any new image you can potentially change things like this. Okay. Same thing with, here's another example like that. Okay. Yeah, so you can see that over the past few slides, I was mostly talking about deep learning because kind of that's what has made the market for data scientists and business analysts pretty alluring for a lot of folks, and hopefully that interested some of you take up business analytics. So one obvious question you can ask at this point is, why don't we just learn deep learning? And the answer is not that deep learning is a substitute for machine learning. It's actually it's also a tool, okay, just like other machine learning tools that you'll see. They're all grounded in ideas from statistics and calculus and probability, right? So you want to have that grounding first before you fly. It's not really a comparison of deep learning versus machine learning. Deep learning is actually one of the tools in the machine learning toolkit. And so this course is going to introduce a bunch of techniques or revisits a bunch of the techniques. And we may even spend, if we have time, talk about deep learning as well. But there's a complementary course that some of you, if you're interested, you can take it. It's going to look at specifically deep learning models. Okay. So some specific architectures for specific situations like time series forecasting or something else. Any questions at this point? Okay, if not, let me briefly mention what to expect in this class, and then we will talk about k-nearest neighbor and decision trees. So what is the learning goals, right? So it's not really learning goals at the lecture level, it's a learning goal at the end of the class. So it doesn't matter whether you have already done 572 or you're simultaneously taking 572 or any other data science related course. The objective of this class is that by the end of this class, you can, have that vocabulary, the familiarity, and be able to somewhat, at least semi-formally, discuss different nuances of different models. Okay, or maybe you may have to sometimes create your own custom model given the idiosyncrasies of this particular data set that you have or particular business setting that you have. Okay. One of the goals is to achieve a little bit more deeper understanding into the tools of data science that we use. For example, you may be using PCA, or you may be using association rules, or you may be using random forests. Really understand, when they can fail, when will they perform, and so on. Okay. Of course, by the end of this class, again, you will be equipped with a bunch of statistical models, and there's a slight distinction between models and algorithms. Algorithms are a way to estimate the parameters of the models. Okay, so if you think of a logistic regression model, that's a model description, but you also want to figure out how to compute those parameters. So maybe sometimes there could be some gains in understanding the algorithm, how the algorithm itself works, in addition to the model. Okay. And also, hopefully, you'll have some experience by trying out a suitable project that you like and maybe you want to expand your skill set in. Okay. What is not expected? Okay, and if you have very high goals, then it's just temporary goals a little bit. It's not realistic to have become the expert in machine learning. Okay, so machine learning is quite vast area with lots of subdomains, and that's why you have these other complementary courses, for example, natural language processing, for example, deep learning, for example, causal inference and econometrics, and so on. So you will not be, it's unrealistic to expect that you will become the expert. And also it's unrealistic to expect really advanced level programming skills. Okay, so you have some programming skills coming into the course. You'll be able to hone them certainly a little bit, but that's not the focus to make you way better in programming. Okay. Will not be spending much time in deep learning, if at all. As I said, it's one part of many techniques in the machine learning catalog, and there's a separate course on it. But if time permits, whenever I can make the connection. Okay. And yeah, so writing skills and things like that, presentation skills. Hopefully, we'll hone some of it in the assignments and in the project but it's not at the level of a professional, technical paper. Okay, so that's not the focus of this class. Okay, so if you think of different reasons why people want to use machine learning, okay, broadly you can classify them into three sets, actually two sets, but then let's talk about three sets. One of them is exploration, and this is where I think people who have heard the acronym EDA or exploratory data analysis. So this first part is exploration. So you really want to, if you have a large data set, okay, high dimensional just means a lot of attributes, okay, a lot of attributes, like hundreds or maybe even thousands of attributes. Okay, so if you want to just explore and understand, patterns. Okay, patterns again are some commonly occurring, recurring things. Hey, these attributes appear together, or these attributes lead to this class all the time. Some patterns that you want to discover. So that's all exploration. And there's some connections to reducing dimensionality and so on. So that's not super critical, but in general, exploration is one focus when somebody wants to use machine learning in a business context. Second one, is the most, I guess, more popular one, is prediction. Okay, and so we'll spend a ton of time on prediction actually in this course. Prediction is just, as we saw in the teaser, it's all about trying to learn that function h. Okay, that's a model. H is a model given the data set B, right? And hopefully, if we have h, then we can reuse it, hoping that past is similar to future. We can reuse h and then therefore make good forecasts and use a forecast for making business decisions. And slightly different variation of that, which is also a business need, is sometimes you want to prove or disprove certain hypotheses that you have about your market, about your product, about your whatever the situation is. And sometimes you also want to know what are called causal relationships. Okay, so this is the reason why it's bucketed slightly differently from prediction exploration, is because there's a need for explanation. Okay, you're not just interested in throwing hundreds of attributes into a opaque box which will spit out what the forecast is. Okay, like for example, the stock price is going to go up or not, but also to understand why would the stock price go up, for example. Right? So explanation is the why part. Okay, why is the forecast this? Why is your prediction that? And that needs additional tools, which we may not have time to cover in this course. For example, you want to make a causal link. Causal link just means, hey, here's the cause for this effect that happened. We will most likely not be making those links in while making predictions. In predictions, we are only going to be making associations. Okay, if attribute in an input attribute is high, maybe it's highly correlated with the output label being of some value. So we're only going to be looking at association analysis mostly in for many of the methods, but a big business need is also to understand causal relationships. Okay, hey, if I change pricing to from $10 to $20, this is how my demand is going to change. Okay, yeah, so in terms of topics, as I said, we're going to mostly looking at the prediction bucket. So many of these topics some of you are familiar with, some of the topics some of you are familiar with. So the list is here. Today we'll be looking at nearest neighbors and decision trees. Okay, so it's on the same bullet point here, but there's a comma, supposed to be a comma here. But there are two techniques that we'll see today. Okay, and there are many techniques. As I said, by the time you see 10 techniques, you have that common language, common pattern of what's going on, what's nuance, what's the difference between technique 1 and technique 2. Okay, and the second bucket we'll cover in this course is exploration. And so I guess you can call it unsupervised learning. Here are some examples: Gaussian mixture models, k-means clustering, principal component analysis, and some other unsupervised techniques. Okay, so independent component analysis and so on. So any questions about what I discussed? It was a quick overview motivation of different considerations for taking the course, learning goals, topics, and what's happened in the ML arena over the past decade. If there are questions, you can always unmute yourself. If you have questions about the logistics of the course, you can unmute yourself and ask, or you can always use the chat. Okay, if not, we'll start with a topic which which concerns k-nearest neighbors. It's called instance-based learning, and we'll define what is instance-based learning in a few slides from now. But let's start with the teaser example that we had, right? So the example that we saw like half an hour ago, which was basically you have a class and you don't know how you're going to get graded, but you know what attributes will be considered while getting a grade, okay, like homework, exam, project, attendance, whatever. And what you have been given is this historical data set, okay? So where you see what happened with homework, what happened with exam, what happened with attendance, and eventually that led to some grade, okay? So here's the example data set, and we said, okay, instances each data point. So I mean, you can include the name as well, but although the name is not useful to predict the grade. And attributes are these feature values. So, and instance space X is the set of all possible feature values. So, like here it's 4 feature values. So all sets of 4 feature values, 4 tuples, would be the instance space X. Okay. So like for example, if each feature is taking 2 values, then there'll be 2 choices here, 2 choices here, 2 choices here, and 2 choices here, for a total of 16 different attributes possible. And so for each of the 16 different attribute combinations, you want to be able to say, hey, what grade is possible, for example. Right. So the label space is a set of all possible outcomes, whatever the grades are. Maybe let's say there are 3 grades, A, B, and C. Then those are the labels, okay, or the label space. An example is pair of instance as a pair of instance and its label. Okay, so X comma Y. And as I said earlier, if we have a data set, so this is a generic representation, a generic example, so without the superscript. But if you want to talk about a specific example, then the ith example, let's say the ith row here, would be X superscript I and Y superscript I. Okay, so the second row would be X superscript 2, will be after this, and Y subscript 2 will be just this. Okay. And as I said earlier, we make an assumption that there is an underlying function that maps from the instance space or the input space to the space of labels. And so that's how data set is generated. So we don't talk about how X's themselves came about. X themselves came about. Okay, and we're going to talk about how X's came about later on when we talk about generative models. But here there is no, we only talk about an input instance space. So so it doesn't matter, there's many different little x's that are possible in this capital X set. Okay, and for each one you take it and then pass it through, or give it as input to this function f, and you'll generate a label. Okay. And maybe if you do it 100 times, then you'll have a 100-row data set that you can generate. Okay. And so now what you have is only that data set, just the xi, yi's. You don't know what the f is. And then the problem is to create a hedge which hopefully imitates or approximates or maybe is equal to f as much as possible. Okay, so that's what we want to do. Okay, that's the learning objective. So learning here just means go from D to a hedge. Okay, so hedge depends on what hedge we learn, depends on what data set we have, and hopefully hedge is as close to whatever f was, which created these y's from x's. Okay, I think we just talked about this earlier. So so the learning process is just to get this function. Okay, just get this function hedge. Okay, so if you think of, so the function hedge, that search procedure to find that function hedge could be complicated, could be simple, and we'll look at some examples. But it's just at the end of the day, if you really abstract it out, it's just a function that maps from the inputs, those attributes to that output, okay, the class label, A, B, and C, for example. And so what we're going to do is figure out how to create hedge. Okay, so we'll do that using 2 example techniques. or two techniques for this session. First one is the k-nearest neighbor method, and the second one is the decision tree. Okay. So is the problem clear? Because we're going to now talk about getting into details of solutions or ways to create or ways to learn H. And so I want to be clear on what the objective is. Okay, certainly, as I said, you can unmute yourself and ask a question if you want, or you can use the chat. I'll be monitoring the chat. So we've been given a data set D, and here I'm just using a bunch of brackets and braces here. So x1, y1 is that pair, example 1, and x superscript m and y superscript m is example m. Okay, m, just think of m as 100. Okay, so m is just although we introduced it first time in the slide, just think of m as 100. So we have 100 examples. Okay, so 100 examples constitute this data set D. Okay, and as I said, xi's belong to, so this notation here, this E type of notation here, it is to say belongs to. Okay, it's a short form for belongs to. You could write explicitly xi belongs to x, but instead of that, applied mathematicians use the symbol as a shorthand. Similarly, label yi belongs to this set of labels. Okay, so this is the set of all possible attributes. So of course, one of the attribute vectors has to belong to a set of all possible attribute vectors, and each label should belong to the set of all possible labels. Okay, so that's the capital X and capital Y. Okay, now, since we are talking about KNN, here's going to be the intuition. Okay, so this is the training data that's given. Okay, now let's say we don't do anything. Okay, we are lazy. But now, so which means that we didn't do any work to create that black box, that function H. But now suddenly we've been given a example X prime. Okay, X prime, just think of, we didn't want to put a superscript, let's say 101 or something. Let's just call it X prime as a generic thing that may or may not be there in the training, that may or may not be there in the D, but you just got some new X prime for which you are supposed to tell me what the class is. Okay, Y prime. Okay, we don't know what the actual class is, but we want to predict. Okay, and our best guess is, let's say, call it Y prime. Okay. So we didn't do any work. We didn't create a H beforehand. So what should we do? Okay. The answer is, okay, I didn't do anything. I just got this data. I didn't do anything. You're asking me what is the label for, or what is the class for this input or this attribute vector X prime. What I can do is go and look back in my data set. Now, I can, I got X prime, I can take the X prime with me and then go to my data set D and see, hey, how close is X prime to any one of these inputs that are already there in the data set? Okay. Maybe I'm lucky and that X prime is actually equal to X1 itself. Then I can say, hey, for X1, I know the output should be Y1. So I can just produce Y1. Okay. But in general, if given an X prime, I can go through my data set and figure out which X prime, so which X superscript 1, 2, or I is most similar to this input, okay? And then use its observed output, okay, as a prediction. Okay? So that's the clever part. The lazy part is that, given this data set, we didn't really construct a H beforehand. Okay? So we didn't really do any work. The clever part is once you get a query for some X prime, you go back to your data set and then do like a potentially a linear scan, which just means look at every row. Hey, is it close? Is it close? Is it close? Maybe not close. Oh, maybe it's close. And then you pick the most similar one. Okay, maybe if you have several similar ones, pick the one which is the most similar. Okay. And in particular, why, you can say, hey, why use the most similar one? Why don't you use a few more? Okay, so you can relax that exactly as you're thinking. So you can say, you still have the data set, you didn't do any work at test time, or you've been given this data set, now you've been asked, make a prediction for a new data point X prime. You can just say, hey, let me find not just the most similar one, but several similar ones, and then I can just average the observed labels or observed classes for these multiple similar instances. Okay. So is the idea clear? Is, the idea was you're being lazy, so you didn't create a model, but at test time or at an evaluation time where somebody asks you, hey, give me a label for a new data point, you can just go back and see somewhat similar instances, and then whatever the labels were, you just pick them, average them. It makes pretty intuitive sense. Average them and then produce it back as, hey, here's a label for the input that you gave. Okay. So I use the word similar, so we'll have to kind of disambiguate what similar is. But otherwise, once the moment we can define or a little bit more formally or make it mechanical what is meant by similarity, then we're almost done. Right? It's just look up, find similar things, and look at their labels and just return it back. Okay. So that's the k nearest neighbor approach. So how do we measure similarity, right? So again, we're going to use an idea which is called a similarity function. Okay, so it's just formalizing what we intuitively know. How do we say two things are similar? Maybe if two input instances are similar, maybe I'm going to assign a score which is high if it is similar. Okay, so let's say let me go back several steps. Yeah, so let's say this vector, attribute vector here, the one highlighted, is similar to the next attribute vector. So if I give these two as inputs, like let's think of them as collection of strings or maybe even a vector or whatever. If I give those two as inputs, hopefully there's a function which can say, hey, the score is high, which means similarity is high, okay, some high number. But instead, if I give the first feature vector and the third feature vector, maybe its similarity is low. And so if I give those two as inputs, then the function should return some low number. Okay, so now this function is a function of two inputs, right? So two inputs. The first input is also a feature vector, and the second input is also a feature vector. Okay. So that is represented, two inputs is represented using this cross product notation. Okay. So I don't know if some of you have done databases. I know some of you have it as a required course. Cross product is just so if you think of X, X and X is a set, right? It's a collection. Collection set is all the same word, okay, formally as well as informally. So X is a collection of attribute vectors. This X is also a collection of attribute vectors. It's just saying that a function of two inputs is formally represented as, hey, it's a function that goes from take one thing from here, take one thing from here. Given those two things, I'm going to produce a real number. So this, bold-faced R basically just means I'm going to produce a number. Okay, so a real number just is a number which need not be just integers or need not be just discrete 0, 1, 2. It can be 1.1, 3.3, whatever. Okay. So that's what this is a short form for that. Okay. So all it's saying is we have a two input, okay, bivariate function which takes two instances, two instance vectors, and produces a score. Okay, so that is needed to accomplish this, right? You want to say, if you have that k, that function, then you can say, hey, what is similar, what is dissimilar. Now the second part is also that how do you pick this multiple instances, right? How many should I take? Just one? Should I take 2? Should I take 10? Should I take 100 similar instances, right? So if your data set, let's say I think previously I said m, let's say, is 100. Okay, so this multiple similar instances, should I take 2 or 5 or 10? That's a question, and you can call that the parameter k. So in k nearest neighbor, the k is a parameter which is saying how many similar instances do you want to look up to make a prediction. So so another quick thing is we're calling these parameters. Okay? Parameters are just configurations, choices that determine how your model is gonna process any new input. Okay, so these parameters are kind of objects that you need to have, okay, in addition to the data set. So as I said, we have the data set, but in order to determine the output, we need the similarity, some notion of similarity or similarity function. We also need to know how many neighbors we want to look at. So that's right. So you can see here that just having the data, we cannot answer this without specifying how many and what is similarity. Right. So that's why those two are parameters of this model or this technique. Okay, so let's start with something simple. In the sense that we know these two are parameters. Let's ignore similarity function for now. Just for now, let's not ignore, but let's think of something simplistic. Okay, so let's say we have a similarity function which, given these two two input feature vectors, says, hey, it's similar or not similar. So it's like a binary. It's like a binary response. Given two inputs, it says, hey, it is similar, or some other two inputs, it will say, hey, it's not similar. Okay, then that hedge function, remember that's the function that we want to trying to get, right? That hedge function for any new test input, this is how we're going to define it. Okay, so we could have written 3 lines of English to say the same thing, but this is the first exposure to, I guess this slide has a bunch of exposures, but the exposure to a little bit of a shorthand notation to say the same thing, which is take the, take the sum over all those data points. So this I here, okay, belongs to Kn of x prime is a set of all similar feature vectors, okay, similar to x prime. Okay, set of all feature vectors which are similar to x prime that are available in your data set. So remember, if I said data set has 100 examples. So let's say given an x prime, my similar examples are example 1, 5, and 10. Okay, only 3 similar examples out of these 100 examples which are similar to my input. Okay, then the summation is over those 3. The summation is over those 3 examples. Okay, and then there's one more term here. So this term here is just saying what is the value of yi for that example I. Okay, so actually let me I want to quickly show you, there's a bunch of things happening there. So so I hope folks are familiar with Python a little bit. So okay, sorry. Right, so this is what we are supposed to. So this hedge function basically. Let me just call it hedge of x prime. That's what we're gonna create. So it's saying, even tab it, but what we want to do is find similar examples in the data set. Right? Okay, let's say they are 1, 3, 1, 5, 10. So remember the data set has 100 examples, rows, right? So it has 100 examples. So find similar examples. Okay, so let's say that was 1, 5, 10. Okay, then what we're saying is so that Kn of x prime is equal to this set. Okay, 1, 5, 10. In that slide there was a Kn of x prime. That's this set. Okay, let me not even write twice. That's this. Okay, then what we do is there is a comment it out. So there is this notation there. Okay, it's a short form, by the way. Notation is just a short form. Okay, there it says y I is equal to y. Okay, so what is this notation? It's just a notation saying for each value that y can take. There's no for loop here, but let's say, okay, let me write it. Fix a value that y can take. Okay, let's say that y can take a value, grade A. Okay, then we want to say so this one of this just means, hey, in the example number I, okay, I is equal to 1, is y, let's say, is y1 equal to a. Okay, so that's what this is. So 1 of the square bracket of yi equal to y is just saying, hey, is y1 equal to a? Similarly, we'll ask the same question. Is y5 equal to a, y10 equal to a? Okay, the answer is, if it's true, we'll take 1, or if it's not true, we'll take 0. We'll take 1 or 0, and so on. Okay. So what I'm trying to say is that that term indicator, so this, by the way, this one is called indicator of whether yi is equal to y, is just saying, hey, pick some value y. Okay, let's say y takes value a. Is y1 equal to a, y2 equal to, y5 equal to a, y10 equal to a? If it is a, you take the value 1. If not, take the value 0. Okay. Now, let's say y1 is, let me say what y1, let's say y1 is equal to a, y5 equal to b, and y of 10 equal to a. And in between there are other observations, but we don't care about it. And we also, for now, don't care about x's for a second. So let's say this is our some information about the data. Okay. By the way, can everybody see what I'm writing in the text editor?
Yes.
Yeah, okay, good. Yeah, sorry, I didn't want to lose everybody. So all I'm saying is this function first finds some similar examples, and then we are just trying to find, count, actually, we're trying to count number of these examples which actually say, it is A. Okay, similarly, you can actually do this thing, B, and check whether it is equal to B, equal to B, equal to B. Okay, and here we know, y1 is equal to A. We know the answer, right? It's actually true. Here it's actually not true. Here it's actually true. Okay, and so what we'll do is there's this. We'll come back in a second. What we'll do that, and similarly here, this is false, and so we'll take value 0. It's true, and here it's false, right? So given that this is the case. Okay. So is this clear what's going on? So this is just a shorthand for indicator of whether y is equal to a specific class value. Okay, so let's say there are only two class values, A and B. Then it's just asking how many of your similar observations that you picked, the labels of them are equal to class value A. How many of them are equal to class value B? How many is because you compare each one of them and then sum them over. If you see here, the sum of these 3 is just 1. And you can see here, the sum of these 3 is equal to 2. Okay. So that's this indicator. Okay. And the count is just exactly this, sum over all these similar examples that we picked. How many of them are equal to A? How many of them are equal to B? And then we are saying find the maximum among those, all possible values of Y. Let's say capital Y, a set of labels can only take values grade A or grade B. Then, for grade A, we got this value, this summation, to be equal to 2. And for grade B, we got the summation to be equal to 1, right? So maximum between 2 and 1 is 2. And arg max of that is the class label which got the highest points. Okay, so let me again switch back to that text pad to say, hey, arg max over, over A, comma B of sum for A and sum for B. Find between these two. Let me just call this equal to right. So from these indicator functions, we found what the for each example it is, 1, 0, 1. If they sum them up, 1, 0, 1, it's 2. And if sum between 0 and 1 and 0, it's 1. Okay. So argmax just means find the max. Okay. Find the max over A and B, which is basically find the maximum between sum A and sum B. That is actually sum A, and what is the class label corresponding to the max, okay, which is A in this case. Okay, so that this is the operation arg. Okay, arg max. Is that clear? So let's. I think some of this is probably new to some of you, so please ask questions if it's not clear. I can repeat. Okay, so some of you are saying it's clear, then it's just now at this point, it's just return arg max. Okay, let's say let's call that variable arg max, or let's just return arg max. So that's what we're doing. So this is find similar examples, okay, and then this is sum their labels, basically. Sum or count the labels, that's what's happening here up to this point. And then here, I guess, find the max and max. Okay, so that's what is happening. And then you just return that. Let me zoom out a little bit to show you the full function. Okay, so you find some examples, sum their labels, so sum their labels for each of the possible labels that you can have, which is check whether they're equal, how many of them are equal to A, check how many of them are equal to B, find the count corresponding to the higher the label with a higher count, and then that's the label that you want to return. Okay. Okay, so what we've done here is use K. Okay, so K is in my write-up it was 3, right? There were 3 examples I picked, 1, 5, and 10. Maybe there were a few more examples, but 1, 5, or 10, implicitly I just assume that they are the most similar, and so there I have used one of the parameters, K is equal to 3. Okay, I still haven't used explicitly a similarity function K. I did use a similarity function in the sense that when I chose the K nearest neighbors, I already said which 3 are the most similar. So implicitly, I did use K, but there are a couple of other ways to explicitly capture K. Okay, so if the K is just binary, hey, this is similar, this is not similar, then this is how your KNN classifier would look like. KNN function would look like. But if you have a more interesting K, then there are other ways to deal with it. Okay, so which is I'll discuss that in a second. But let's pick K is equal to 3 again. We're not changing the example. In the same example, what is the worst thing that can happen when you pick K is equal to 3? Okay. The worst thing that can happen is, one of the worst things, okay, not the worst thing, but one of the worst things that can happen is the most similar instance is actually similar to, happens to be similar to X prime. But the second and third similar instances are very different from X prime. Okay, are very different. But still, they happen to be, in terms of the most similar, they happen to be the most similar. But in terms of absolute sense, they are like, quite different. Okay, they're different. They're like the worst among the best, right? Or actually, it's the best among the worst. Okay, so all the other instances are very dissimilar to this X prime. But among all these dissimilar guys, just as the second and third instances happen to be the closest in terms of similarity. So if that is the case, then you can understand that if you do a 3 nearest neighbor prediction, the labels for these second and third instances may mess up your prediction, right? This is an example where your 3 and n, the choice of 3 is going to potentially negatively influence your performance. Okay. So given this observation, the question is, can we say that 3 nearest neighbor is always better than one nearest neighbor? Okay, so that's the question. And some people have already answered no. At this point, you should be actually asking, hey, how do you know what is better? Like, what is the metric to say one is better than the other? Okay, so we haven't yet actually discussed that well yet. Okay, but let's we're going to dwell on it in a few more slides actually. So one of the answers is no, that one of the students said 3NN is not always better than one nearest neighbor. Okay, and right now the short answer is it's true. Okay, a priori we cannot say that 3NN is always better than one nearest neighbor. Okay, and that's because we did not even talk about what's better. Yeah, so as somebody says in the chat, Srinivas says in the chat, a model that predicts better on unseen data is better. Okay, so one candidate definition of what is better is that this KNN model, what for example this 3NN model, should do well, score well on some unseen data compared to the other one. So okay, if you have two models and you want to say which one is better than the other, one candidate way to do it is to, hey, pass unseen data to them and see which one is actually reflective, which one is closer to the original underlying f function. Okay, so but one way to fix this, okay, where you're not changing the choice of k, but you can change the h, if you have when you're not changing the number of nearest neighbors, but you can change your prediction model to use the similarity function a little bit more explicitly. Okay. So let's say the similarity function is producing a score, which is not just, hey, similar or dissimilar. It's actually producing a score, like now, 10 units if it's very similar, maybe 0.1 units if it's very dissimilar. Okay. Then, so there are actually some properties that the similarity functions satisfy. For example, they're generally like positive, and maybe high value means more similar, low value means less similar, and so on. If that's the case, then what you can do is, while doing the summation, you can actually add a weight parameter. Okay, it's like a weighted summation. It's like a weighted average. So it's just saying that, hey, if x, you gave me x prime, for which I want to produce a label. I got, these three examples, which are the top three similar. But let's say x1 is the one which is, so let's say the first one is the most similar to it. Then the k value for that one will be super high. The second and third similar examples are not that similar. So, okay, for them, the k value will be somewhat low. Okay, so that will ensure that the label for the most similar one is what's going to be influencing your prediction. Okay, so that's because you're summing them up. So the influence of the most similar one would be upweighted, basically, and the second and third similar one will be a little bit less weighted. So you'll not be completely off, although the second and third similar ones are actually not that similar. Okay, so there's an explicitly we can add k here. Okay. Any questions about this part? Okay. So let's look at a slightly different version of the problem. So far, we've been talking about this class labels, a set of class labels, grade A, grade B, or some discrete values. So instead of that, what if they were numeric values? Okay, so the class labels themselves. So basically, we're thinking of some sort of a regression setting, okay, where the output that we care about is actually some continuous number, between, let's say, 0 to 100, or maybe 0 to 200. Then what do? The fix is to do the following. You, instead of taking an argmax, okay, argmax over all the possible labels, grade A versus grade B, what you do is just take the weighted average of the scores in the examples. Okay, so for example, just go back to our running example where we said instance number 1 in the training data, instance number 5 in the training data, instance number 10 in the training data constitute the top 3 nearest neighbors. Then, of course, the similarity scores are same as before, but those instances, their scores, their sorry, not scores, but their outputs, okay, are numeric. So you just take the weighted average of them. So it's called a weighted average because you can see that the denominator is dividing by the sum of those similarity scores. Okay, so let me actually illustrate that again using a quick note here. All I'm saying is if y1 is 10, y2 is 5, and sorry, not y2, but so let's say these are the three. 1, 5, and 10 are the nearest neighbors, by the way. Okay, out of this 100 example data set, and let's say this is 20. And so you have this k value of x1 comma x prime, okay, is let's say 2. Similarly, okay, let's make it 10 and 1 and 1. Okay, so just to keep the same example, where the most similar one is the one which was actually kind of relevant. The other two ones, although they are similar, they're not that similar. Okay, that's why the k score, the score given by this 2 input function k is low. Okay, then your prediction h of x prime is basically 10 times 10 plus 1 times 5 plus 1 times 20, okay, divided by 10 plus 1 plus 1. Okay, so this is what I meant by weighted average. Okay, so let me just put a bracket here. Okay, so the weights are just these k values. So k for x1, k for x5, k for x10, those are 3 values. And then those k values are just getting multiplied by the numeric values of the outputs observed in the training data, which were these 10, 5, and 20. Okay, so now you can see that the weighted average, the weight is higher for the first example. Okay, so that's going to massively downweigh the impact of having, let's say, 20 for an instance which is not that similar to this query instance. Okay, is that clear?
Professor Chao this side. So Professor, I'm not able to understand how we are assigning, I mean the 10, 1, 1, how are we calling these three as, using these three as weights? Because weights are normally shows the frequency basically for a particular number in a data. I mean, that's my understanding, but
yeah, good point. So I'm using the word weights and it's an overloaded term. It means different things in different contexts. So I just mean, think of the similarity, right? So x prime is the one which is given to us, and we want to find its label, right? We want to find its prediction, okay? And we are in the regression setting. So it's not class labels, but these are just numeric scores. Okay, new numbers are, yeah, the output is numeric. Okay. Now all I'm saying is this the similarity function produces 3 numbers, right? Because I want to find the similarity of x prime with the first I actually find the similarity with all the data points, all of my 100 data points. But let's say 1, 5, and 10 are the top ones. Like, in fact, let's just put the other ones. So x, let's say 2 and x prime, let's say 0.01 and so on. Okay, so all the other ones are like below the cutoff of 3. We want to look at the top 3, and so the top 3 are these. Now, all I'm saying is I'm going to consider these as a way. I'm going to use these while averaging these 3 scores. Remember, if I was not, let's say I want to make prediction at the new x prime. I know these 3 are the most similar. The first instance, 5th instance, and 10th instance. I know their labels, 10, 5, and 20. If I want to make one candidate prediction, I can just say, hey, 10 plus 5 plus 20 divided by 3. Why is that? Because, hey, I have 3 possibilities and I don't know which one to, suggest. I can always, pick one of them or just take an average.
Average.
So that average is an unweighted average. Okay, it's equally weighing between all 3 options. So it's like saying 1/3 of 10 plus 1/3 of 5th plus 1/3 of 20. Okay. Instead of that, here we are saying this is going to be unequal averaging, or what I call weighted averaging, where I'm going to say the first number will be multiplied by 10 divided by 12 instead of 1/3. The second number will be multiplied by 1 divided by 12 instead of 1/3. And the third number will be multiplied by 1 divided by 12 instead of 1/3. So I'm going to give higher weightage while averaging to the first number. Okay. So why is this averaging still correct? Is because 10 divided by 12 plus 1 divided by 12 plus 1 divided by 12 is equal to 1, which is the same as 1 divided by 3 plus 1 divided by 3 plus 1 divided by 3, which we were doing earlier. If you're doing 1/3, 1/3, 1/3, we can still, that's the usual averaging. Like 10 plus 5 plus 20 divided by 3 is just saying 1/3 times 10, 1/3 plus times 5 plus 1/3 times 20, right?
Right.
So similarly, what we're doing is instead of 1/3, 1/3, 1/3, we're going to give higher weightage to the first point because it is the most similar.
Most similar.
Yeah.
And
that's what we're calling weightage. Okay, those weights in model parameters are different. Yeah.
And Professor, one more thing. So here the 10-1-1. So basically, the 10-1-1 is like we are defining this to understand the similarity. Function,
right? So
just
think of, you have access to, so as I said, these are parameters to the KNN model. So you need to have a def k which takes x1, x2, or let me not use, let's call it x1, x2, and produces return similarity between x1 and x2. So you need to have access to some function like this.
Yeah, so basically, so Professor, this similarity is the distance, right? So here we are getting the distance, this 10.
It's like the negative distance, okay? If the farther distance is high, but similarity is low. Think of it that way.
Okay, yeah. Okay, now I understand. Yeah, makes sense. Thank you.
Yeah, good. Anybody else has a question or maybe similar concern? You can tell me. Okay, so there's a question in the chat. Higher weights are given to closest neighbors. Yes, higher similarity values for closest neighbors. Yeah. So similar, closest neighbors. So that's what it means, right? So we are defining neighborhood by saying they're similar. Okay? Only if they're similar, they're neighbors. Okay. Only if x1 and x prime have a high k value, whatever this similarity function values, then therefore they're the closest. Okay. So the top 3 closest are these 3 in this example. Okay. So because the k values are high, we're going to call them neighbors, and therefore also closest neighbors here. And how do we assign those weight or scores? So how did we get k itself? That's a good question. So there are several candidates. I'm just jumping the gun here a little bit. You can say, hey, return. So if x1 and x2 were vectors, okay, then one example is e to the power. It's very similar to Gaussian function. I don't know if you remember a Gaussian distribution. So you can do e to the power minus of the absolute value of x1 minus x2, okay, something like this. So okay, let me actually give an example here. So let's say k of, let's take a one-dimensional example here. Actually, let me cut this out. Okay, so let's take numbers 1, 2, 3, 4. Okay, so let's say they are numbers, and we want to say how similar are these numbers, right? So you can define k for number 1, number 2. I mean, this is just one dimension, but we can make it to 2 dimensions and so on later. We can just take, hey, return the absolute value of num1 minus num2. Okay. So if I do this, so then you know that if distance between 1, 1, or not distance, sorry, similarity of 1, 1. Actually, let me just do it in a different way. 4 minus that. Sorry, this is again the confusion between distance and similarity. So let's say I do this. So then the similarity between 1, 1 is, take number 1 as 1, 1 minus 1 is 0, 4 minus 0 is 4. This is one return. So what is the similarity between 1 and 4? Okay, that's 1 minus 4 is 3. Actually, maybe I should use 3 here. Then this is actually equal to 0. Okay, for example. So just give me a sense of, give 2 inputs. Somebody has to tell you how to, how similar they are. So here is an example function. I just arbitrarily chose some function here. It's 3 minus absolute value of number 1 minus number 2. Okay, why that function? Why not something else? So in general, people use this function. Okay? I mean, this is not the only function, but this function, which just says, and this is where linear algebra comes into the picture. Okay, so think of x1 and x2 as vectors, two vectors. Okay, which means something like this, right? So let's say x1 is equal to 1, 1 is a vector. Let's say x2 is 2, 2. This is another vector. Okay, some two vectors. Then x1 minus x2 is what? Minus 1, minus 1, right? So just a subtract element, subtract coordinate wise. And then this of x1 minus x2, what is this called? It's called the norm. Okay, so I didn't specify the norm. Let's say it's 2 norm. Okay, so 2 norm. Okay, so what is this? This is just square root of first coordinate square, which is 1 plus 1. Okay, so let me again write it. Square root of
1 plus 1.
Yeah, minus 1 to the power 2. It's the definition of Euclidean distance, by the way. That's what this is. Sorry, this should not be 0 there. And then again, same thing. This is a norm, definition of an Euclidean norm. Okay, Euclidean norm is just it's like the Euclidean distance between that vector and 0. So it's like minus 1, minus 0, minus 0, individual coordinates, the whole square, sum them, and then square root of them, right? So that's a Euclidean distance. You might have seen this type of distance function somewhere. So that's the value, and that if you see, this is equal to what? Square root 2, right? So 1.4 or something, right? And then the similarity is e to the power minus 1.4. Okay, that's the similarity between these two vectors. Okay, now what would the similarity between if k of x1 and x1 itself? Euclidean distance between x1 and x1 itself would be 0, right? And e to the power minus of 0 is this 1. Okay, and this number is actually going to be strictly less than 1. So if it's the same point, then there's some similarity level, and if there are different points, the number the score is going to be lower and lower. Okay, it's going to be closer to like 0.5 or something. I don't know. Yeah. Anybody else has a question? So how do we assign this k? We have not defined. I mean, this is just an example where I said, hey, this is one. This is one example that you can try, and here's one example for two, one-dimensional situations and so on. But we have not discussed that in the slides. Okay. Well, we missed a break. Okay. Let's see. Yeah, so let's take a break for 10 minutes and again resume. Okay, we'll resume at 5:05. And do let me know around 1.5 hours to take a break. Okay, through chat or something. So we'll resume at 5:05. Okay, so let's actually resume. So there's not much more to k-nearest neighbors than what we've discussed. We pretty much discussed the two key ingredients to do this lazy prediction for any given query. The first one is the choice of k itself, and we'll come back to this in the next slide, which is the number of neighbors you want to consider, and also the choice of the similarity function. Okay, so which we didn't see any explicit examples except for some that I created in the text pad earlier, in the text editor earlier. But this is some function that you need, which says, hey, given two input instances or two feature vectors, how similar they are. Okay, so and that's what defines neighborhood. Okay, that's what defines neighbors. Two things which are super similar to each other or very similar to each other or high score as given by this function k, then they are considered neighbors. Okay. I think I also briefly mentioned that the similarity function needs to satisfy some properties. For example, it'd be nice if it's symmetric. So if I change, if I give x1, x2, or rather give x2, x1 as the inputs, I should get the same similarity score. So x1 is as similar to x2 as x2 is similar to x. Okay. And also, you would like that the similarity function is, at least non-negative, so that this weighted averaging makes sense. If you have negative weights, that's not exactly weighted averaging. Okay, in the most common sense. So. Okay, now let's come back to this original point of the choice of k. So here you can see on the left side, we've chosen one nearest neighbor method. And so what are we trying to show in this figure? Okay, let's focus on this figure. We have a two-dimensional data set. Okay, so 2D data set, which means that the input or feature vector is of 2 dimensions, okay, 2 coordinates. So think of the x coordinate as the first feature dimension and the y coordinate as the second feature dimension. Okay, and these dots here are just grid points, like the small dots there are grid points. So the actual examples themselves are here, in circles. Okay, some circles are colored blue, and some circles are colored orange. And okay, so the blue coloring is for class blue, and orange coloring is for the class orange. Okay, so there are 2 classes here. So the coloring of the circle indicates which class that data point belongs to. Okay, now why do these small dots also have a coloring? We'll get to that in a second. Blue or orange, but you can see these black lines here. Okay, so those black lines are basically the decision boundary. Okay, so the decision boundary is captured by these black lines or black contours or curves here. What they correspond to is that at that point in the instance space, remember this is a 2D input instance space, at those points on those black curves, if your query point, if your query x prime was on that black line, it's unclear whether you're gonna say the label is blue or the label is orange. Okay, so there's a tie happening. So the moment you are in the in any other point, let's say in this orange region, if your query point is here, then for that point, the one nearest neighbor, for example, is the closest one is this orange, and therefore you can that the label for that query point is orange. Okay, but for the ones on the exact line, for example, here you can see that there's a orange there and blue here. So the label for the point exactly on that black line is unclear. Okay, so and you can see that this is the decision boundary, and maybe some decision boundaries don't make sense. For example, maybe this blue, like this contour here or the blue island here, it may be that blue is just a very rare occurrence. You should not actually mark this as blue. This whole region probably is orange. Okay, for example, that could be your intuition, and maybe k is equal to 1, the number of nearest neighbor. One nearest neighbor is not really getting to the right decision boundary that we were hoping for. Okay, now here's another example where k is equal to 15. Okay, so here k is equal to 15 leads to a decision boundary which is somewhat smoother. Okay, first of all, it doesn't have multiple curves which are not connected to each other as you see on the left hand side. On the right hand side, there is a much smoother curve. Of course, it's non-linear, it's not even linear, but it's a much smoother curve. Is able to put majority of the orange circles on the top left and majority of the blue circles on the bottom right. Okay, and so higher the number of k, it's kind of smoothing the decision boundary. Okay, so then we have a question. So what happens when k is equal to the number of points? Okay, so if you think of our data set had 1,000 points, sorry, 100 points, right? So what if we choose k is equal to 100? what do you think is going to, what do you think is going to be the decision boundary? Anybody has an answer? So the question is, if k is equal to 100 and if you have 100 data points, what happens? Like, where is this black curve going to be? Okay. Because k is equal to 1, we already saw it's on the left side. K is equal to 15, some number, it's on the right side. But what if k is equal to 100 when we have only 100 data points? Okay, so let me discuss the thought process. So if k is equal to 100, little k is equal to 100. Yeah, somebody has already answered pretty much. So k is equal to 100. What happens is, for any test point, if you only have 100 data points, and if little k is equal to 100, then you're saying, hey, all the data points are my neighbors. Okay, so if all the data points are your neighbors, then what could the color be? The color will be the color of the data points with the highest, data points which have the highest of the one of these orange or blue colors. So let's say orange is 40 and blue is 60. Then if all the 100 are your neighbors, then the highest color is actually blue. So you'll say blue, and you'll say blue irrespective of where you are. Okay, it doesn't matter where on the page on this 2D space your query is. If you are considering 100 neighbors, you'll always have the color blue. So you will not see actually a decision boundary. So it's a kind of a vacuous question or some sort of degenerate situation where the decision boundary is like nowhere. Either it's like surrounding all points, as somebody said, or basically it's not visible because there's no boundary between oranges and blues. Okay, so that's the situation where k is equal to 100, but I didn't say anything about the similarity function. Okay, so of course I simply implicitly said the similarity function assumes that if k is equal to 100, the similarity function will, one variant of similarity function will say, hey, for any given pair of points, it will say, hey, you are a neighbor. Okay, because there's no other answer to say. Everybody, is a neighbor for any query point. Okay, but you can also do another thing here. So let's look at the numeric version. So what you can do is the summation over the k nearest neighbors of x prime. What you can do is you can do a summation over all neighbors, say all data points. Okay, forget about finding nearest neighbors. What you can do is just say, hey, you gave me an x prime query. Let me find its similarity to all my 100 data points, and then do this weighted average. Okay, so if I do this weighted averaging, then then there is no notion of like nearest neighbors in the sense that I have kind of smoothened it out. Okay, so the data points which are kind of nearest in the sense that they are the most similar, they'll have higher weightage, and the points which are not that similar and therefore not that much of nearest neighbor, they're going to have low weightage. And so even without even if you choose k is equal to 100, if you have a reasonably good capital K similarity function, you will still get some interesting result. Okay, so not the vacuous result of, not the default result of all blue that I was talking about earlier. Okay. Any questions at this point? Okay, so I think if you have questions, certainly drop me or Prashant an email, or come to our office hours and we can discuss. So let's actually finish up this set of slides. So let's come back to this. Previously I was, we did mention, learning, but we didn't really kind of say what type of learning actually we're doing. So when you have input and output space given by, let's say, capital X and capital Y, and we assume that there's a function behind the scenes that got us the Y for every given X, okay, in the data set. And given now the data set, we want to find a H which approximates F the most, or is ideally you find F itself, or find something which is as close to F as possible in terms of giving us Y's for any new query feature vector. Then this is called inductive learning. Okay, so you're basically doing induction or inductive learning, which just means, hey, I saw some examples based on that for a new test point. What should be the prediction. Okay, so it's induction in general. Okay, so for example, think of collaborative filtering as an example. Okay, so collaborative filtering is a specific application. We're going to talk about it quite a bit potentially later. But what is this application? We want to say, hey, we have a data set like this, which is a little bit different from the data set for the grading example that we were talking about. It's basically for each user, what movies they, the movies that they saw, and for the movies that they saw, they gave explicit ratings. And so let's say the explicit ratings, and by the way, this is not typically what you would have with Netflix. Netflix doesn't probably ask explicit ratings these days. But let's say we have movies with explicit ratings for the user. Then inductive learning is still the same. It doesn't have to be that X to Y format. Here, the function, f is basically taking a user and a movie as input and is trying to say, hey, what is the rating that this user would have predicted? So this user would have given. Okay, so that f function is still this unknown function that gave, on the data set, hey, 2 for user 2 movie 1, a 2 for user 2 movie 2, a 3 for user 2 movie 3. That was the function that gave these black numbers as these, this black colored numbers as these training data set. Now, can you tell me what would be the function's prediction, or what would be h? Hopefully h is similar to this underlying f. And so if I have this h, then I can say, hey, for user some u prime for movie 1, what would be their rating? Okay, so if I guess that, maybe I'll collect those ratings and pick the movie that is highly, has a high NF estimate, and then those estimated the movies with the high NF estimates are the ones maybe I'll recommend. Okay, so that's an example of inductive learning. The learning exhibited by KNN is called instance-based learning. Okay, so these are slightly different. This is a class of learning algorithms that avoid induction. Okay, so we'll talk about induction a little bit more when we talk about decision tree approach, maybe in the next lecture. But basically, what we're trying to do is construct what should be the prediction. Okay, hypothesis. So don't worry about hypothesis as the word here. Just say construct prediction. Okay, so we're constructing our predicted label on the fly from the training data. Okay, so in KNN, there's no learning of a model excessively. Like, we got the data, we kind of were lazy, we didn't do anything. Only when a query came, we went back and said, hey, what are the similar things, and then average and do some weighted averaging and make a prediction. Okay, so that's on the fly kind of constructing of a solution and using training data. Okay, of course the downside is that if you're going to do on the fly, if you have your time to compute whatever you're trying to compute, let's say the prediction, may be dependent on how big your data set is. And so this is a notation used in basic computer science, which is just saying, hey, the time, so computation complexity, just think of how many similarity computations do I need to do? How many times do I need to invoke this similarity function k, right? So if I have to find the most similar, the top 3, for example, if I have 100 data points, I'll have to compute the similarity with all these 100 data points, right? But if I had 1,000 data points, I have to find similarity with all these 1,000 data points. So there's if you have bigger and bigger amount of data, isn't like more examples in your data set, then you need more time to find just exactly those top 3 nearest neighbors, right? So that is represented by this big O notation. It's a notation from basic, in computer science. It just gives you a sense of, it gives you a sense of how much the computational, or basically the time complexity of your approaches. Okay, and here we are using it loosely. We're just saying that you need more time if you have more data, more examples in your data set. So that's why the dependence is on M, which is the number of examples in your data set. Okay, so it just says, the time to compute your on-the-fly solution really depends on how much data set it scales linearly with the number of examples that you have. But the pro is, because you're not really pre-computing a fixed model. So you can, it turns out this KNN approach is actually pretty good as long as you're not in super high dimensions and the data is very limited. Okay, so as long as you're a reasonable number of attributes, and a lot of data, so actually you can do pretty well. Okay, it has really good predictive performance. Yeah, and so in that sense, it does well, and so it is somewhat clever, but it's lazy. So it may take a lot of time if you have a lot of data points. And of course, there are workarounds. So what we presented here is the most simplest narrative. People have figured out how to make, fix the cons, how to improve the pros, how to, judiciously choose the right K, the right, similarity function, and things like that. Okay, so there are a lot of improvements people have done, but we have seen one version, okay, the simplest version here. So the question is, can we do better than instance-based learning? Okay, so which is like, can we do inductive learning? Okay, and in particular, can we do better in terms of can we do explicit generalization and get rid of this computational complexity? Maybe also match or even improve compared to the prediction capability of KNN. Okay, and the answer is yes, and we'll look at decision trees in the next class. Okay, so we look at decision trees as a prototypical example of a method which does generalization, okay, which is inductive, which doesn't do construction of hypothesis on the fly. It builds a model. In fact, the model is a tree-like object, and we're going to talk about what is a tree and all that. And we'll talk about computation complexity. Generalization has its own set of issues, so you have to talk about test errors and so on. And so we'll do that next class. Okay. So any questions at this point?
Professor, I have one question. So can you go back to that partition slide where we were comparing the KNN 1 versus 15?
Yeah.
So Professor, here I was thinking, like if we talk about the regression part of the KNN, there won't be this type of partition, right? And this type of partition we get, like here we have two partition, I mean two classes.
Yes.
So we're getting two classes because we have in the Y category, we have two classes, say top and high, like I mean low or medium type, only two categories. If I have multiple categories, then I'll get multiple sections, right?
Yes. So just to clarify, so decision boundaries only make sense for classification problems. So you will not have decision boundaries the moment you're talking about regression. Okay, so this oranges, blues are exactly the two classes that you're talking about. So since there are only two classes, there will be a decision boundary. Even if you have three classes, there will be decision boundaries. I mean, they may not be like separating two things. Of course, they may be separating three things, and so on. But yeah, decision boundaries exist only in classification settings. And first of all, you can only visualize them in two-dimensional or three-dimensional situations like this. You can't really look at higher dimensional situations anyway. So kind of decision boundary is a nice concept, but in terms of visualization, it's only limited to 2 or 3 dimensions that you can see those demarcating areas. Yeah, but they only make sense for classification. So regression decision boundaries are not there. Yeah, good point.
Thank you. I'm good. Thank you.
Yeah, thanks. So anybody else has any points or comments? So since it's the first lecture, it's hard for me to gauge whether it's super easy or super difficult. I know for some folks who have not seen the math notation, it may be, the notation, the shorthand notation actually is not really the math notation, but like the shorthands saying, hey, similarity function has 2 inputs and 1 output, it's just a notation that's kind of universal. And so it's easy to kind of communicate this with other data scientists or other business analysts or even just the general audience in the machine learning community if you kind of use the same language, okay? For folks who have seen it, it should be a recap, and you can kind of ensure that it's not incompatible with what you know already about KNNs or other kind of topics that we've dealt with today. Yeah, I think if you have questions, as I said, come to our office hours, and we'll try to discuss what prerequisites or some other extra readings I should do. But again, one last thing I want to repeat is that the reason why first assignment is a little bit later is because I want you guys to spend time on linear algebra, calculus, and introduction probability. Okay, so understand conditional probabilities, understand expectations, understand, for example, what is entropy, matrix vector multiplications. So for example, similarity function is at the end of the day will give you a square matrix. Okay, so for every pair of points, every pair of inputs, you can get a matrix, and it's going to be m cross m, where m is the number of data points. Okay, so if you have an m cross m matrix with a bunch of numbers in there, then that's a similarity matrix. Okay, and that similarity matrix is kind of the opposite of a distance matrix. Okay, if distance is small, similarity is high, and if similarity is low, then distance is large. Okay. So anyway, so there's some ideas about matrix algebra, linear algebra, some ideas about calculus already in this lecture. We haven't seen much of probability. We'll see that potentially, next lecture or the lecture after that. Okay. So do try to spend some time on that and talk to Prashant and the TA or myself about the prereqs. Okay, if there's nothing else, thank you. Next lecture is actually quite delayed because of next Monday being off. But our office hours and potentially registration, if Prashant is going to announce something, it's going to be on Blackboard, and try to make it to the office hours or registration. Okay. Registrations are decided by Prashant. Depends on what the audience wants and things like that. Okay. Any questions? Last minute questions? Ebook. Okay, so there's a question about ebook. So in addition to these slides, there are two books, right? There are two reference books that you might have seen in the. Let me just flash that. Right. So these books are ebooks. They're just PDFs. You can get the EPUB or those versions as well. Both are free as well as you can buy them. The second book, Introduction to Statistical Learning, is a great introduction if you don't want to if you're not super familiar with the notation that we've used, for example, today. Elements of Statistical Learning is a good standard book that many data scientists are familiar with. So it's good to look at that as well. So both cover similar topics and of course have great overlap with what we're covering in the lectures as well. A lot more elaboration, a lot more detail, a lot more examples, for example, especially in the second one. So they're good references to read. Okay, so you can pick up the KNN part or the addition tree part or examples and look at them. Where can we find the slides? You can just find the slides here. The third link is the slides link. If you click on that, you can just get the collection of slides. So you'll see both the PowerPoint as well as the PDF version that I was using today. And for refresher, as I said, the first couple of weeks you should really do this, because if you don't do this, you'll have that issue with catching up, in week 3, week 4, week 5, week 6, when rest of the class is moving forward. So I would really suggest look at the first few links. The first, refresher and probability and linear algebra are just YouTube playlists, and they're pretty short, an hour pretty much to go through both of them, or maybe 2 hours max. The others are just some PDF resources for you to kind of recap what are the basics. Okay. And this resource, mind map, is a good resource to kind of understand what are the different parts that you have already seen, maybe in 572, maybe in some other course, big data, and other places. It'll give a sense of like what are the moving parts in this machine learning journey that you're undertaking. Okay. So maybe next class I'll open this up and show it. Okay, then have a good rest of the evening. See you guys next time. Bye.